Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2023 paper of Chemistry Unit 4. In the first question, we have a question about the rate equation. Now there are two equations from which we have to find the rate equations which could be correct. So from the first equation, now both the equations are the same. So if I multiply 2 on this side, I'll have the same equation as the top. So both of the rate equations will be the same. The rate equation does not depend on the ratio. It just depends on the what are the reactants and products. It does not depend on the number of moles of reactants. So B is not our option since this and this are different. So we can cancel this and this since we have a power of 2 here and power of 1 here. Now in the rate equation only the reactants can be involved. However, in C and D the product is involved in the rate equation. This is not possible, so we can cancel C and D. We'll only be left with A. Now we have to monitor this reaction continuously. So if I want to do it continuously, I cannot do titration. Titration can only be done after some time, or you can collect the mixture after some time. So it will be discrete, not continuous. So A is out. We can do B. Since we have nitrogen dioxide, this is a colored compound, while nitrogen monoxide and oxygen are colorless. So this is brown in color. So we can do this. We cannot deal with mass change since we can also do it with volume change since there are 3 moles of gas on the left and 2 on the right. In this case it's 1.5 and 1. So we can do that. There won't be any change in mass since everything will be in the reaction mixture. So there is no mass change. So B is our answer. Now in question 2, we are asked the half-life of a first order chemical reaction is, and we have 4 options to choose from. The first, the half-life is the time taken for the concentration of a reactant to halve. So C is the answer. The rate constant, it doesn't have to be the rate constant to halve. The rate constant is unchanged at a certain temperature. And A is also incorrect since it will take more than that. So the time taken for the reaction to complete will be more than double of this, since the curve is something like this. So the more it goes, the rate of reaction will decrease. And D is not the option since the time taken for the concentration of a product to double might vary from this. This is the exact definition of the half-life. Now in question 3, we are given the reaction E plus 2F goes to G plus H. The rate determining step or the slow step is this reaction. So the reactants of this reaction will be involved in the rate. So we have one E and one F. So the rate equation will be K times the concentration of E times the concentration of F without any power. So A is our answer. Now for question 4, we have to find which graph shows the entropy of a substance as it changes state from solid to liquid to gas. The entropy in solids is the lowest, while the entropy in the gas is the highest. Since solids are like this, so they are in order. So the order in solids are much higher than gas. Gas has a lot of random motion, so it has a high entropy. Now the change in entropy from solid to liquid is smaller than the entropy change from liquid to gas. So when we go from solid to liquid, the vertical jump is less than when it goes from liquid to gas, which should be longer. This is because the change in disorder from liquid to gas is much higher. And another thing is, as the temperature increases, the entropy continuously increases. So A and B are not the answer, since we have horizontal sections over here. If the temperature increases, the entropy also increases, so something like this. Now between graph 3 and 4 will be the answer, since the vertical section when we go from liquid to gas should be higher. So this is the liquid portion, this is the solid portion, and this is the gas portion. The jump between gas and liquid, this jump over here, must be longer than this jump. So this must be longer than this. In graph 3 this is shorter, so this is wrong. So graph 4 is our answer. Now moving to question 5, we have two flasks P and Q. P contains argon and Q is in vacuum. We have to assume that argon behaves as an ideal gas and has no intermolecular forces. We have to talk about how the entropy and energy of the system will change when the tap is opened. If we open the tap, the argon was only in flask P. If I open the tap, the argon will be in flask P and Q. So the entropy of the system, or the disorder, will increase. So option B and D are out. Now if I look at the energy of the system, since this is an ideal gas, the temperature will not change over here. So the energy of the system must be unchanged. So C is our answer. Now to question 6. We are asked, when hydrogen and oxygen are mixed in a flask, there is no reaction, and when a platinum gauze is added to the flask, the mixture explodes. And from here it can be deduced that in the absence of a platinum gauze, the hydrogen and oxygen mixture is this over here. So we have to think about its kinetics and thermodynamics. So the platinum gauze gives you the activation energy in this case. So it needs the activation energy from somewhere else, but if it gets that activation energy, the reaction will continue. So if the reaction continues after I give the activation energy, it must be thermodynamically unstable. So C and A are not the answer. It must be thermodynamically unstable. But since the reaction does not occur without the activation energy due to the platinum gauge, so in this case it's not kinetically unstable. The reaction is kinetically stable. If it was kinetically unstable, the reaction mixture would explode even without the platinum gauge. So B is our answer over here. Now on to question 7. We are given a Born-Haber cycle for sodium oxide. We have to find which energy change Y denotes. So Y is this. The change we have over here is the oxygen going from O without any charge to O2 minus. So this is the sum of the first and second electron affinity. The first electron affinity will convert this oxygen gas plus 1 electron into O minus gas. This is the first electron affinity. And the second electron affinity will turn that O minus gas and electron into O2 minus gas. So this is the sum of first and second electron affinity. C is our answer. Now we have to find which expression gives the enthalpy change of formation del F del HF. This over here is the formation enthalpy of Na2O, Now I'll consider the lines clockwise. So the ones that are clockwise will be on one side and the others on the other side. This over here is anti-clockwise. The arrow is anti-clockwise. So this is on one side and all the other ones. So this arrow is clockwise, this arrow is clockwise, this one is also clockwise. So is this and this. So we have x plus w plus v plus y plus z. U over here is the formation enthalpy. So del HF is the addition of x, w, v, y and z. Well, so D is the answer. We have x, w, v, y and z over here all in addition form. So D is our answer. Now on to question 8. We are told that an ionic compound is found to have some degree of covalent bonding. We have to find the cause of the covalency and how the lattice energy obtained will be different from the theoretical value. The Born-Haber cycle is the experimental value. So the experimental value becomes more exothermic than the theoretical value. It's more negative. So it can be A and C, B and D are out. And this is due to the cation polarizing the anion. So the cation's positive charge will distort the electron cloud of the anion. This causes the covalency. So we say that, this is cancelled. So B and C are not the answer. It will be more exothermic. So A and D can be the answer. Now between A and D, we have to talk about how the anion is polarized by the cation. So A is out since we are talking about the cation being polarized by anion. This is wrong. The anion must be polarized by the cation. So D is the answer. Now moving to question 9. We have to find the equilibrium constant expression for this reaction. So Kc over here will be, on the top we'll have the concentration of the reactants to the power of number of moles. So this. Now if I look over here, Fe3O4 is a solid. In the equilibrium constant, we only consider the liquid and gases since solids won't have a concentration. So this and this will not be involved. On the numerator we'll have hydrogen gas to the power of 4 due to this 4 in the front, and this will be divided by the concentration of steam to the power 4. So D is the answer. Now in question 9b, we have to write down the effect of the equilibrium constant if the small pieces of iron are replaced by powder and if the temperature is increased. Now this is an exothermic reaction. In an exothermic reaction, if the temperature is increased, the value of the equilibrium constant decreases, and in endothermic reactions this is the opposite. So in endothermic reaction, if the temperature increases, the value of K also increases. And we have to take into account that the value of K, the equilibrium constant, is only dependent on the temperature. So using the iron powder will not cause any difference. So A and C are not the answer. Kc will be unchanged when iron powder is used. And since this is an exothermic reaction, we have to follow this. So an increase in the temperature will cause the value of the equilibrium constant to decrease. So this is wrong. This is the answer. D is the answer again. Now for question 10, we are told that equal amounts of ethanoic acid and methanoic acid are mixed. We have to find the conjugate acid and base. Now between ethanoic acid and methanoic acid, the one with the lower pKa value is the stronger acid. If the pK is smaller, the value of Ka is larger. So the smaller the pKa value, the larger the acid dissociation constant, and larger the acid dissociation constant, stronger the acid. So methanoic acid is the stronger acid. So in a reaction between ethanoic acid and methanoic acid will act like the acid and ethanoic acid will act as the base. So methanoic acid will lose an hydrogen while this will gain an hydrogen. So the acid is HCOOH. This is the acid. So option A and C might be correct. B and D are out. And the conjugate base for this is HCOO minus. So option A is our correct answer. So base 1 is the conjugate base of the acid 1, while the base CH3COOH has a conjugate acid of CH3COOH2 plus. A is our answer. Now on to question 11. We are told that a 1 mole per dm cube solution of ethanoic acid is diluted with distilled water. We have to talk about the degree of dissociation of the acid and the pH of the solution as the distilled water is added. As the distilled water is added, the concentration of H plus will decrease. So the dissociation of ethanoic acid, which is this reaction over here, since the concentration of H plus decreases, this equilibrium will shift to the right. So the degree of dissociation will increase. C and D are not the answers. Also, since the concentration of H plus is decreasing over here, the value of pH will increase, since a decrease in hydrogen ion concentration causes an increase in pH. So A is our answer for this question. Now moving to question 12. Here we have to find the pH of a saturated solution of magnesium hydroxide at 25 degrees Celsius. The solubility at 25 degrees Celsius is this value over here. So the pOH value. Now before we do that, we have to consider the fact that magnesium hydroxide has 2 OH minus per each magnesium ion. So the dissociation is like this. So we have 2 moles of OH minus per 1 mole of magnesium hydroxide, and the solubility is this value over here. Since magnesium hydroxide is a strong base, the dissociation will be complete. So the concentration of OH minus will be twice the concentration of MgOH2. So this value over here. Now using this, I'll find the pOH. This is minus log base 10, 2 into 1.1 into 10 to the power minus 4. From here, the pH will be the pKa minus the pKw. The pKw value at 25 degrees Celsius is 14, since minus log base 10 of 1.0 into 10 to the power minus 14 is basically 14. So we have 14 minus log base 10. We can just calculate this, and if we do this, the value will come out to be 3.66. So the pH is 14 minus 3.66, which comes out to be 10.3. C is the answer. Now for question B, we are given the saturated solution of magnesium hydroxide at 25 degree and 100 degrees Celsius are compared, and we have to find the difference in the pH values of this solution. If we look over here, the concentration is higher at 100 degrees Celsius. So C and D are out, and between A and B, B will be the answer, since the pH will become higher the pH, as we increase temperature, the pH scale moves to the right. So basically the pH values tend to go higher. You can calculate this right now as well. For at 100 degrees Celsius, the pOH will be minus log base 10 times 2 into this concentration. So 4 into 10 to the power minus 3. This will be 2.10, and the pKw value will become minus log base 10, 5.5 into 10 to the power minus 14. This value will be 13.26. If I calculate 13.26 minus 2.10, this will come out to be 11.16. This is 11.16. The previous pH was 10.3. So the pH is higher and the concentration is also higher. So B is the answer. Now moving to question 13. So we have propanol and butane, and we are told that even though the compounds have the same molar mass, there is the propanol has a higher boiling point than butane. So if I look at the structure of them, propanol is CO. So this is propanol and this is butane. In propanol there is a electronegative oxygen over here, so this will cause a permanent dipole moment. You might be tempted to talk about hydrogen bonding, since there is a hydrogen here and an oxygen here, but this hydrogen over here is next to a carbon. For hydrogen bonding, this hydrogen has to be next to a nitrogen, fluorine or oxygen, which isn't the case over here. So we don't talk about hydrogen bonds here. The London forces on propanol is not stronger, since both of them have similar masses. That leaves us with only one option, which is option B. So the permanent dipole forces are due to this difference in electronegativity over here. Now into question 14, where we have the structure of an ester. We have to find which two compounds are needed to form this ester. So this is the portion that we get from the carboxylic acid, and this is the portion we get from the alcohol. So from the from the carboxylic acid we get this part. So this was the carboxylic acid, and from the alcohol we'll have this part over here. So we have an OH here, and the rest of the compound will be the same. This has 1, 2, 3, 4 carbons over here. So this is okay. Instead of carboxylic acid, we could have also used acyl chloride. In this case, we have used acyl chloride. So we have a 4-carbon acyl chloride, so butanol chloride. C and D are not the answers. We are using butanol chloride. And for the alcohol, we are using this thing over here. So we have CH over here, another CH here, CH3, CH3. The longest carbon chain is 4. We have to keep the alcohol in the lowest possible place. So this is carbon 1, 2, 3 and 4. So we have a alcohol on the second carbon and a methyl group on the third carbon. So we have 3 methyl butanol. So B is our answer. Now for question 15, we are given samples of ethanol and propanol which are added to separate testing tubes containing iodine dissolved in aqueous potassium hydroxide. and then they are heated gently, and a pale yellow precipitate will be formed. We have to find for which. So this test is the test for the group CH3C double bond O. This test of iodine dissolved in potassium hydroxide will turn pale yellow if this group is present. Now in ethanol we have CH3C double bond OH, and for propanol we have CH3C double bond O CH3. So this is ethanol, this is propanol. Both of them contain the group CH3CO, so it will turn yellow for both of them. Now question 16 is about a chromatogram, and we have to find the RF value. For this we'll have to use our meter rule. We'll place our meter rule over here, measure this length, consider this L, and we have to find this length. So if I consider this L0, this will be L1. The RF value will be L1 divided by L0 or L0. If I do this, this will be around 0.7. You have to be careful of where you take the length from and up to. So this length over here divided by this length over here, sorry, the other way around, the red one divided by the blue one will be the RF value. So it comes out to be 0.70. Now moving to section B. In question 17 we have a reaction between hydrogen peroxide and iodide ions in acidic conditions. In this case we are told in the first question that the rate of this reaction may be obtained by adding a fixed volume of sodium thiosulfate and a few drops of starch solution. The sodium thiosulfate will react with this iodine over here until the sodium thiosulfate is used up. After that, the iodine that is produced will react with the starch solution, producing a starch iodine complex which will have a blue black color. So we'll be able to observe a blue solution, or the solution turned blue after some time, and by finding the time taken for this blue solution to appear, we can find the rate of the reaction. The rate will be 1 divided by the time taken for the solution to turn blue. This is the rate. So this is how we write down our answer. We talk about how the sodium thiosulfate reacts with the iodine that is being formed in this reaction, and when all of the sodium thiosulfate is used up, this iodine, the iodine that's still produced, will react with the starch solution, and when that happens the solution will turn blue, and we record this time taken for the blue color to come, and the rate of reaction is 1 divided by this time. And this is it for this question. Now moving on to part 2, we have to find the rate equation for this reaction. So between reaction 2 and 3, the concentration of H2O2 is the same. The concentration of H plus is almost the same, and the concentration of I minus is almost doubled, and the rate of reaction also doubles. So the rate of reaction in respect to I minus is 1. So with respect to I minus, rate order of reaction is 1. Now we'll look into reactions 1 and 2. In this case, the concentration of H2O2 is halved, the concentration of I minus doubles, and the concentration of H plus is the same, and this causes the reaction to be the rate to be the same. Now, if only I minus had changed and it was doubled, the rate of reaction should have doubled. However, halving this causes this to remain the same. So, with if the order of reaction with respect to H2O2 was 0, this should have doubled. So, this should have become 0.00362, but it still remains the same. So, this is due to the H2O2. So, the concentration of H2O2 being halved causes the rate to be halved, while doubling this causes it to double. So, if we have half into 2, this will remain the same. So, this is 1. So, with respect to H2O2, order of reaction is 1. Now, if I look between reaction 3 and 4, this is doubled, this is doubled, this is almost the same, and this causes the reaction rate to double. The doubling of the reaction rate is due to H2O2. However, the doubling of H plus does not cause any change. So, with respect to H plus, order is 0. So, the rate equation over here is K times the concentration of hydrogen peroxide times the concentration of I minus. This would be the rate. Now for the next question, let me fix this. Now for the next question, we have to find the rate constant. The rate constant is the value of K at 293 Kelvin using results from run 1. So we have to use this result. So the rate over here is 0.00181. Then we have K times the concentration of hydrogen peroxide, which is 0.0210, and we multiply the concentration of I minus in this experiment or the first run. This is 0.0198. Now to calculate K, I'll move this 2 to the left. So I get 0.00180 divided by 0.0210 multiplied by 0.0198. If we calculate this, we get a value of 4.35. We also have to calculate the units. Now, if I calculate the units, the rate over here is given in mole per dm cube per second. This is the this is K over here, and we multiply 2 concentration with it. The concentration are given in mole per dm cube. So we move this 2 to the left. So the units of K will be mole per dm cube per second divided by mole per dm cube times mole per dm cube. We can cancel out one of the mole per dm cubes on the bottom with the top, and we'll be left with the units for K, which will be dm cube per mole per second. Since if we move this to the top, so if I move the denominator to the top, their powers will be multiplied by -1. So the unit of K is dm cube per mole per second. Now we'll move to the next part of this question, part B. We are told that the student carried out a second series of experiments at 313 Kelvin and found out the rate of reaction was 4.45 times faster than that at 293 Kelvin. We have to calculate the activation energy for this reaction using the Arrhenius equation, which we are given below, giving our answer to an appropriate number of significant figures. So this is the Arrhenius equation where ln K, where K is the rate constant, and now we have a constant on the other side. This remains constant no matter what the other values are. We can write this down as C. Now at 293 Kelvin, we know the value of K is this over here, 4.35. So ln 4.35 is equal to minus activation energy divided by RT. The value of R is 8.31 and the temperature is 293 Kelvin. So 8.31 into 293 plus C. And at 313 Kelvin, we have ln 4.35 multiplied by 4.45. The rate constant is 4.45 times more than that. This is equal to minus activation energy divided by 8.31 into the new temperature, which is 313, plus C. Now we have two equations. We can subtract one from the other. So we can have 1 minus 2. 1 minus 2. This will be ln 4.35 minus ln 4 into 4.35. On the right, we have minus EA by 8.31 into 293 plus activation energy divided by 8.31 into 313. The C's cancel out. Now on the left, we'll have ln 4.35 divided by 4 into 4.35. On the right, if we calculate this, it will come out to be, we can take EA by 8.31 common over here, and then we'll have minus. So inside this, we basically have minus 1 by 293 plus 1 by 313. On the left, we have ln 1 by 4, since we can cancel the 4.35s out. And on the right, we have EA by 8.31 multiplied by minus 20 divided by 97. 20 divided by 91,709. Ln 1, from here we can directly calculate activation energy. This will be ln 1 by 4 multiplied by 8.31 divided by minus 20 divided by 91709. If I calculate this, the activation energy comes out to be, oh wait, it was 4.45. This was 4.45, not 4. This is ln 1 by 4.45. Now we have to calculate this. If we calculate this, it will be plus 56,887 joule per mole. Now we have to use appropriate number of significant figures. In this case, we have to take the significant figures of the data value with the lowest. So the data value is this temperature over here given in 3SF, this temperature over here given in 3SF, and the ones we used in calculations. This one is given in 3SF, this one is given in 3, this one is also given in 3SF. So the values we used for the calculation are all given to 3 significant figures. So the activation energy should be given to 3 significant figures. So if I do that, I'll get 569.00 joule per mole. So 56,900 joule per mole is our answer. If you could also turn it to kilojoule per mole if you want, but this is fine. Now moving to question 18, we have a question about lactic acid over here. This is our 6 marker. We are told that lactic acid may be obtained from ethanol in a laboratory by the 2-step synthesis shown below. Now we have to explain why the lactic acid formed in muscles is optically active, while the ones obtained using laboratory synthesis is not. The lactic acid can be optically active because if I look at it, it has a chiral center over here. So this carbon over here is a chiral center. It has 4 different groups bonded to it. One group is a CH3, the other is a H, the other is an OH, and the other is COOH. So this carbon over here is a chiral center. So due to that carbon being a chiral center, lactic acid might be optically active. And before that, we need to define what optically active means. Optically active molecules are those that can rotate the plane of polarization. So if there was a polarized light falling onto lactic acid, it might. So this is a test tube full of lactic acid or a beaker full of lactic acid. If polarized light uh, hit this, so if it was polarized like this, the lactic acid will rotate the polarization by a bit. So before it was straight like this. After going through the lactic acid, it will be bent a little. It will rotate the plane of polarization. And it can do so because it has a chiral center. Now, after that, we have to explain why the lactic acid obtained by the laboratory synthesis is not optically active. So I'll write down what I've said so far. So far we have written about how optically active means that the molecule can rotate the plane of polarization of polarized light, and how lactic acid can be optically active since it has this chiral center over here. Now we'll talk about how the laboratory synthesis is not optically active. So the lactic acid found from this synthesis is not optically active. We have to explain why that is the case. So in optically active compounds, there are 2 types of them. One is positive enantiomer and the other is negative enantiomer. So we have positive enantiomers and negative enantiomers. So in this molecule, if I moved one of them, so if I had an OH over here, for instance, and the CH3 over here, this will be, so if I consider this to be the positive enantiomer, this over here will be the negative enantiomer. The positive and negative just means if it rotates the light clockwise or anti-clockwise. So depending on that we call it negative or positive enantiomers. Now, if I have equal amounts of positive and negative enantiomers, the light will be rotated clockwise and anti-clockwise by the same amount. So basically, the light will not be rotated since it's being rotated clockwise and anti-clockwise by the same magnitude. So we must have the same number of moles of negative and positive enantiomers when we produce it through laboratory synthesis. This is called a racemic mixture. So we write down how the lactic acid produced by the synthesis contains equal amount of both positive and negative enantiomers, which forms a racemic mixture. Now we have to explain why this is the case. Now, if I look at the mechanism for this first step, this Cn minus can attack the this carbon over here from this side or from this side. So it can be attacked from either the top or the bottom with equal probability, since this is a planar shape. So we can draw this shape in a single plane, and the Cn minus nucleophile can attack it from outside into the page. So if you want to imagine this, you can imagine sticking a page into your screen, or sticking a pencil into your screen. The Cn minus can attack like that from the top, or you can think about sticking your pencil in from from behind your screen. So it can attack with equal probability from inside and outside, uh, or from the top or bottom if you're considering it like this. So if you have this shape over here, it's like a triangular piece of paper. These are the bonds, and you can think about the uh, Cn minus nucleophile attacking from the top of that paper or from the bottom of that paper. So we have an equal probability of that happening. So we talk about how the carbonyl group over here, this group is planar, and the Cn minus can attack it from above and below the plane with equal probability. So we talk about how the racemic mixture formed because the carbonyl group is planar, and the Cn minus nucleophile can attack it from above the plane or below the plane with equal probability. Now we have to also explain why the lactic acid in the muscles are optically active. This might be due to a lot of factors. A common factor is that natural processes or physical processes often prefer one optical isomer or optical enantiomer over the other. An example of this is this medicine over here called thalidomide. You don't have to know this, but this is just an example of physical processes preferring one enantiomer over the other. So thalidomide was a medicine for treating morning sickness in pregnant women. However, only one enantiomer worked for this. So, for example, the positive enantiomer uh, helped with morning sickness. So, this is why the medicine was made. However, the negative enantiomer had dangerous side effects which caused birth defects in the children whose mothers took this medicine over here. So, the negative enantiomer caused birth defects, while the positive enantiomer helped with morning sickness and had no side effects. So this was one problem with this medicine. So from here we can see a clear example how the body prefers one uh, enantiomer over the other. So we can talk about this in case of lactic acid as well. So this is how we finish our answer. We talk about how in the case of lactic acid produced by muscles, it is optically active since natural processes select one particular enantiomer over the other. So this is how we structure our answer in this question. Now for part B1, we have polylactic acid, which is a polyester derived from lactic acid as the only monomer. And it's also referred. We have to draw the structure of PLA showing two repeat units. So this is one lactic acid. If we look closely, there is an OH group over here, so an alcohol group, and a carboxylic acid group. So it has both. Now, if I have another lactic acid next to it, I'll draw its alcohol close to this carboxylic acid. So we have this on the other side. Now the OH from the carboxylic acid and the H from the alcohol will join together to form a water, and this carbon will form a bond with this oxygen over here. So if I do this, I'll have H3C CHOH. Now similarly, like the alcohol for this lactic acid, the alcohol from this lactic acid will also lose an hydrogen and form a bond with another lactic acid's carboxylic acid part, and then we have C double bond O, and on this side we have O CH CH3 C double bond O, and this OH will be lost to another alcohol group to form water. So this is this is one repeat unit, and this is the other repeat unit. So we have two repeat units of PLA. If I want to draw it nicely, I can draw it like this as well. Now we are told that lactic acid is converted into compound X, which is then polymerized to form PLA. We are given the empirical formula is C3H4O2 and its molar mass is 144 gram per mole. We just have to find the molecular formula. So the empirical formula is C3H4O2. So the empirical formula mass, so if I calculate this, this will be 3 times 12 plus 4 times 1 plus 2 times 16. If we calculate this, we'll get a value of 72 gram per mole. So if I divide the molar mass of this 144 divided by the empirical formula mass, this will be 2. So the numbers over here, so 3, 4 and 2, they will all be multiplied by 2 and we'll get the molecular formula, which would be C 3 into 2, which is 6, H 4 into 2, which is 8, O 2 into 2, which is 4. We have a molecular formula of C6H8O4. This is the molecular formula of X. Now for part 3, we are given a high resolution NMR of X, where the numbers over here are the relative peak area. We have to state what the number of peaks and their relative peak areas, and splitting pattern shows about a structure X. We have only 2 peaks over here. So from this we can understand that there are only 2 environments that the proton or the hydrogen are in. Now we'll talk about what the relative peak areas show. It shows that the ratio of hydrogen is 1 is to 3. So 1 plus 3 is 4. In X we have 8 hydrogen. So we have to times 2 to get 8. So both of this peak area, if we double, we'll get the number of hydrogen in each environment. So in this environment, there are 2 hydrogen, and in the other environment, there are 6 hydrogen. So we get 8 hydrogen in total, 2 in one environment, the 6 in another. We talk about how the relative peak area shows that there are 2 protons. We can write hydrogen over here as well. So 2 protons in one environment and 6 in the other. Finally, we talk about their splitting patterns. Now from the splitting pattern, we see that there is a quartet peak over here. So 4. 1, 2, 3, 4. So this must be next to a 3 so the for this hydrogen or this proton, the neighboring carbon must have 3 hydrogen. And for this, we have a peak with a doublet. So we have 2 lines over here. It represents that there are 3 hydrogen in the, sorry, 1 hydrogen in the neighboring carbon over here. So the carbon neighboring to this protons has 1 hydrogen in it. So the doublet is next to one proton or 1 hydrogen, and the quartet is next to 3 protons or hydrogen. Since the ratio is 1 is to 3, the hydrogen or 1 hydrogen is next to this 3. So there is 1 hydrogen next to this over here, giving it a splitting pattern of a doublet. And for this over here, there are 3 hydrogen next to it. So it has a splitting pattern of a quartet. We can talk about how they must be adjacent to each other for this splitting pattern as well. So we talk about how the doublet peak is showing that there is 1 proton on the neighboring carbon. We can have a S in a bracket since it's the sum of all the carbon, all the protons on neighboring carbon. So if this was the case, so if this hydrogen had, if these 2 hydrogen had 2 neighboring carbons, we'll calculate the number of hydrogen in both of them. So we can write a plural carbon over here as well. And then we talk about while the quartet peak is showing that there are 3 protons on the neighboring carbon. Now we are given a carbon 13 NMR of X where we have 3 peaks. We have to state what additional information that we get from X from this. From this, we get that there are 3 peaks. So we have 3 different carbon environment. Now, if I look at the data booklet for the carbon 13 NMR, we'll also find that this peak over here near 170, this is due to an ester. We can write about that since we are given 2 marks. This only covers one of it. We can write about how this peak is due to an ester in the second. So over here we talk about how the 3 peaks show that there are 3 carbon environments and the chemical shift around 170 ppm indicates that an ester group is present. Now we have to draw the structure of X using the information from part B2 up to B4. We know that the molecular formula is C6H8O4. Now, if I want to divide this into, we have to have symmetry over here since we only have two hydrogen environments and 3 carbon environments. So if I do something like this, so we have 1, 2, 3, 4, 5, 6 carbon. I'll have H3 and H3 over here. So 6 hydrogen in this environment. 1, 2, 3, 4. We cannot do this. We are exceeding the number of hydrogen. If I want to move this out, put double bonded oxygen over here, since we won't have any hydrogen in the central carbon. And I cannot do anything else if this is a straight chain. So we can try it with a cyclic compound. We'll try a cyclic compound since the carbon is to hydrogen ratio is very low. We can take that hint as well. So a 6 carbon chain, 3, 4, 5, 6. If I try this, I'll place the double bonded oxygen over here, H2, H2. So this doesn't work as well. Now I can incorporate, we can try incorporating oxygen into this since we know that there will be an ester. Since we know that there is an ester group, we have this and we have to make this symmetric. So CO like this. I'll place double bonded oxygen on either end. And we're left with this carbon to work with. So we have 4 carbons and we have 2 carbons remaining. So I'll place each of the remaining carbon over here. And if I do this, I'll have a H over here. So if I have this, the carbon ratio of 1:3 is maintained. This will be a doublet. This will be a quartet. We have an ester group over here and here. We have 1, 2, and 3 different carbon environments. So this satisfies all of the conditions that we have found so far. It also matches the molecular formula as well. So this is the answer. Now moving to question 19, we have a statement about carbonyl compounds. We are told that carbonyl compounds are usually reduced using complex metal hydrides such as LiAlH4, and the metal hydrides are reacting by supplying H minus ions, which then reacts with the carbonyl group to form an intermediate, and that the addition of a strong acid in aqueous solution to the intermediate produces a reduction. Since we need to have an H plus after we reduce this, since this only produces H minus, we don't have to go so far. For the first part, we have to state the conditions for using LiLH4. Uh, for using LiLH4, we have to use it in dry ether. We cannot use aqueous solutions of LiLH4 since this will reduce water itself. So we use dry ether. Now we have to complete the mechanism for the reduction of propanol with LiLH4 showing the structure of the intermediate and the final product. So we have an H minus over here. This will have a lone pair. This attacks the carbon over here. Since the carbon is electropositive, this oxygen is electronegative. This will cause this double bond to break heterolytically with the electrons going to the oxygen. So we'll have an intermediate. This over here will be the intermediate. Now we have a dilute acid, or we have a strong acid added to it. The strong acid basically provides H plus ions to it, and we have an O minus with a lone pair. This lone pair over here attacks this H plus, and from here we get the final product. We have CH3, CH3, HOH. So this is the final product. Now we have to explain why ALI ALH4 is H4 reduces carbonyl compounds but not alkenes, even though both have pi bonds. The problem is in alkenes, we have no electronegativity difference between this carbon. So the carbons are not electropositive or over here. In this case, the carbon is electropositive, which allows the H minus nucleophile to attack that carbon. In alkenes, they don't have any electronegativity or electropositivity. So the carbons do not attract the H minus in alkenes. So in this answer, we talk about how the C double bond O bond is polar due to the electronegative oxygen atom. The electronegative oxygen atom causes the carbon to be electropositive, and this electropositive carbon attracts the H minus ions or nucleophile. Whereas in the case of alkenes, the C double bond C, this bond over here is non-polar and cannot attract the H minus ions. Rather, it would repel the ions since there is a high electron density due to the double bond. Now moving to question 20. In the first question, we have to find the entropy change for this reaction over here. We are given the standard molar entropy of the reactants and the products. So the change in entropy of the system will be the entropy of the products minus the entropy of the reactants. So product minus reactants. The products are C2H4 and C2H6. So we'll add both of them. 229.5 plus 219.5, and then we'll subtract the entropy of the reactant, which is 310.1. If I calculate this, I get a value of 138.9 joule per mole per Kelvin. Now in part 2, we have to find the enthalpy change of the reaction. So the enthalpy change over here will be equal, we are given the formation enthalpy of the products and reactants. So we have to remember the formula that the enthalpy of formation of the products minus the formation enthalpy of the reactants gives you the reaction enthalpy change of reaction in this case. So the R is for reactants, the P is for products. If I do this, the formation enthalpy of the product is the sum of both of them. So 52.2 minus 84.7. This is the formation enthalpy of the products minus the formation enthalpy of the reactants, which is minus 126.5. If I calculate this value over here, it comes out to be 94 uh, kilojoule per mole. Since the values are given to 3SF or 1 decimal place, the values are all given to 1 decimal place. I'll also write the answer to 1 decimal place. Now for part 3, we have to calculate the entropy change at 298 Kelvin. The del S surroundings is equal to minus del H, the enthalpy change of reaction, divided by the temperature, which is 298. So this is minus plus 94.0 divided by 298. We'll also give this value to 1 decimal place. This comes out to be minus 0.315 kilojoules. So this was in kilojoule. I can convert it into joules by multiplying 10 cube. This comes out to be 300 plus 315.4 joule per mole per Kelvin. Now we have to find the total entropy change at 298 Kelvin. This will be the summation of del S system and del S surroundings. Del S system was del S system was plus 138.9 and del S surroundings was 315.4. If we add both of them up, I'll get a value of, oh, before we go there, this was negative. My bad. So we have negative 315.4 joule per mole per Kelvin for del S surroundings and positive 138.9 for del S total. So in this case, del S surroundings come out to be minus 176.5 joule per mole per Kelvin. Now we have to calculate the temperature at which the cracking becomes feasible. So the temperature at which del S total becomes positive, or we want the temperature at which del S total is 0. So for any case, if we are asked to find at what temperature a reaction becomes feasible or infeasible, for both cases, we'll calculate with del S total set to 0. The del S system will stay unchanged over here. It will remain at 138.9. And for del H, for del S surroundings, we'll have the del H was 94 into 10 cube divided by the temperature. Now the temperature is the unknown over here. If I move this expression to the left, I'll get 94,000 divided by T is 138.9. From here, I can make T the subject. By moving it to the right, I'll have 94,000 divided by 138.9 equals to the temperature. This temperature over here comes out to be 676.7 Kelvin. Now moving to part B, we are given that 5 moles of butane is cracked at 750 Kelvin. At equilibrium, we have 4.45 moles of ethene and the total pressure is 1.20 atmospheres. So it's ideal if we make an ice table for this reaction. Initially, we had 5 moles of butane and we didn't have any product. We have the change and equilibrium over here. Now we know that at equilibrium, 4.45 moles of ethene is produced. So we also have 4.45 moles of ethane. So the change is 4.45 moles. And for the left, we have minus 4.45. So we are left with 0.55 moles of butane. So this will be needed in part 2. For part 1, we just need the expression of equilibrium constant. This will just be the partial pressure of C2H6 multiplied by the partial pressure of C2H4 divided by the partial pressure of butane C4H10. Now for part 2, we have to find the value of Kp. So in this case, we need the ice table. Now we have found the uh, equilibrium mole ratio. We also know that the total pressure is 1.20 atmosphere. So partial pressure of butane is 0.55 divided by 0.55 plus 4.45 plus 4.45. So this is the total number of moles multiplied by 1.20. This comes out to be, so the partial pressure of C4H10 is this value over here. We can just go ahead without calculating them. The partial pressure of C2H4 will be 4.45 divided by 0.55 plus 4.45 plus 4.45. So instead of this, I can just write down the numerator as 9.45 by adding all of them. This is multiplied by 1.20. The same is the case of ethane. 4.45 divided by 9.45 multiplied by 1.20. From here, we can find the value of Kp. It will be the partial pressure of C2H6 and C2H4 multiplied over here on the top. This multiplied with itself again, divided by 0.55 by 9.45 into 1.20. From here, we find the value of Kp, which comes out to be, this value will come out to be 4.57. Now we also have to mention the units. On the top, we have ATM into ATM, so atmosphere into atmosphere, and on the bottom, we have atmosphere. We can cancel out 1 atmosphere and 1 atmosphere over here. We are left with the unit of atmospheres to the power of 1. So this is the unit of Kp. Now moving to section C, we have question 21. We have gluconic acid, which is a weak acid which occurs in fruit and honey and is widely used as a food additive. We are told that a solution of gluconic acid was prepared by dissolving 4.75 grams of the solid and then making it up to 250 cm cube in a volumetric flask. In the first question, we have to write the equation for the acid dissociation constant Ka using RCOH for gluconic acid. The value of Ka will be, so the dissociation is basically RCOOH being dissociated into RCOO minus and H plus. So Ka will be the concentration of the products in their ratio. So 1 to the power of 1 times RCOO minus to the power of 1 divided by the concentration of RCOOH. This is the answer to this question. Now for part 2, we have to calculate the pH of the solution of gluconic acid. So we have 4.75 grams of this solid, which has a PR of or MR or molar mass of 196. From here, I can find the moles of gluconic acid. This will be the mass 4.75 that we have used divided by the molar mass, which is 196 gram per mole. The number of moles is, if I want to work with exact values, this comes out to be 19 by 784 moles. This is the number of moles of gluconic acid that we are using. Since gluconic acid is a weak acid, we can make two assumptions about it. One of them is that the concentration of H plus and the concentration of RCOO minus is the same. This is one assumption. The other assumption is the concentration of RCOOH initially and at equilibrium are almost the same since the dissociation is very low. So in equilibrium and in initial condition and or the number of or concentration of the carboxylic acid or gluconic acid initially and at equilibrium is the same. So we take these two assumptions over here since gluconic acid is a weak acid. Now, if we take those assumptions at equilibrium, we'll have H plus squared over here since we are considering both of them to be equal. And this will be the concentration of RCOOH. Now we know the value of Ka. So in the next line, I can just write that down, 1.38 into 10 to the power minus 4. This is equal to the value of H plus squared divided by the initial concentration of gluconic acid. We have to calculate that. We have this many moles of gluconic acid being dissolved in 250 cm cube. So the concentration of gluconic acid is the number of moles divided by the volume. So 19 by 784 divided by the volume. Since I want to find it in mole per dm cube, I'll convert that into the 250 cm cube into dm cube. So I have 250 into 10 to the power minus 3 as the volume. The concentration comes out to 19 by 196 mole per dm cube exactly. Divided by that 19 by 196. The concentration of del H plus, the concentration of H plus squared will be 1.38 into 10 to the power minus 4 into 19 by 196. To find the concentration of H plus only, I'll take root over on both sides. The concentration of H plus comes out to be 3.657533461 into 10 to the power minus 3. You can work with less significant figures. This is the concentration of H plus ions. From here, I can find the pH just by placing this value over here. So log base 10 of this value. If I do this, I'll get a value of 2.44. This is the pH that we are wanting. Now for part B, we have a titration curve over here. We have to explain why phenol red is an appropriate indicator for this titration. The vertical section of this graph is from around 7 or somewhere below 7 up to around 9 or 10. So around 6.5 or 6.6 to around 9 or 10. This is the vertical section over here. Now I have to look at the pH range of phenol. This can be found on page 19 of the chemistry data booklet. The pH range of phenol red is given to be 6.8 to 8.4. And if I look into this, the pH range of this indicator falls entirely within the vertical section. So we can use this indicator here. So we write down how the color change in phenol red occurs in the vertical section of this titration curve. Now for part 2, we have to calculate the pH of the titration mixture after adding 35 cm cube of sodium hydroxide solution. For this, we'll have to calculate the moles of gluconic acid in 25 cm cube of its mixture. So we are using 25 cm cube of gluconic acid. So we have to calculate the number of moles of gluconic acid in that. We already know the number of moles of here we already know the number of moles of gluconic acid, but this is in the case of 250 cm cube. So we'll just divide it by 10 to get the number of moles in 25 cm cube. It will be 19 by 7840 moles. And then we have to find the number of moles of sodium hydroxide. In this case, the concentration is 0.105 and we are using 35 cm cube of it. So 0.105 into 35 into 10 to the power minus 3. This comes out to be 147 by 40,000, or this is the same as 0.00365 moles, and this is approximately equal to 2.4234 or 35 into 10 to the power minus 3, so 0.002423 moles. Now the mole ratio of sodium hydroxide to gluconic acid is 1:1. So the number of moles of excess NaOH, so this many moles of sodium hydroxide will be used up to neutralize the gluconic acid, the rest will be excess. So the XX is 0.003675 divided by 19 by 7840. This is the number of moles of excess NaOH. This comes out to 1.25 into 10 to the power minus 3 moles. I have the number of moles of excess sodium hydroxide over here as well. Now I can find the concentration of sodium hydroxide. We have the total number of moles 1.25 into 10 to the power minus 3, and this is in so we have 35 cm cube of sodium hydroxide in 25 cm cube of gluconic acid. So we have 35 plus 25, and now I'll change it into dm cube by multiplying it with 10 to the power minus 3. I'll get 0.02086 mole per dm cube. I have to find the pH. So from the concentration of NaOH, this is equal to the concentration of OH minus. From this I can find POH. This will be minus log base 10 of 0.002086. This will be equal to 1.6807. So the value of pH will be 14 minus 1.6807, which is 12.3. Now in part C, we are given that mixtures of gluconic acid and sodium gluconate are buffers. We have to explain how a solution that contains both gluconic acid and sodium gluconate act as a buffer, we have to use RCOOH for the formula of gluconic acid. Now, in this scenario over here, both gluconic acid and sodium glucanoate, so RCOOH and RCOONA, both gluconic acid and sodium glucanoate are in large reserves. And now I have to show what happens when I add alkali and acid. So when acid is added, uh, RCOONA, or from RCONA I get RCOO minus. So this basically happens. It's in this form over here. So the RCOO minus reacts with H plus to form RCOOH. This is a reversible reaction. You could throw it in. You could show it with one arrow like this, or show it as a reversible reaction. You can do both. And this is when acid is added, and when alkali is added, so basically OH minus, we have RCOOH plus OH minus. This will be in a equilibrium with RCOO minus and H2O. Now, since both RCOOH and RCOONA, or we can just write down minus over here, they are in large reserves. So both of them are in large reserves. We have written about that. As they are in large reserves, the concentration of RCOOH or gluconic acid and sodium glucanoate does not change much. Or we can say that the ratio of their concentration, so which is RCOH is to RCOO minus, remains almost the same. And if they remain the same, the pH does not change much. So this acts as a buffer over here. Now for the next question, we are given that the concentration of gluconic acid is 1.55 mole per dm cube. We have to calculate the number of moles of sodium gluconate that must be added to 1 dm cube of this solution. In this case, we can use the Henderson-Hasselbalch equation, which is this equation over here, where the pH is equal to pKa minus log of the concentration of acid divided by the concentration of base. The pH over here is 3.71. We need the pKa. We have the Ka of gluconic acid, which is this value over here. So pKa is minus log base 10 of 1.38 into 10 to the power minus 4. This is pKa. And then we have minus log the concentration of acid by base. Since we have 1 dm cube of sodium gluconate, the concentration and number of moles will be the same. The concentration of the acid is 1.55. I need to find the concentration of the base. The conjugate base is RCOO minus. From here I can find the concentration, which will be, sorry, I can move it to the right. And on the right, we'll have minus log base 10 of 1.38 into 10 to the power minus 4 minus 3.71. If I calculate the right hand side, this comes out to be 0.1501. So 1.55 divided by the concentration of the conjugate base is equal to 10 to the power 0.1501. The concentration of RCO minus is 1.55 divided by 10 to the power 0.1501. From here, the concentration of RCO minus, which will also be equal to the number of moles since we have 1 mole of it. So number of mole divided by the volume, which is 1 dm cube, is equal to 1.097. So 1.10. So the number of moles of sodium gluconate RCOONA is equal to 1.10 moles. This is the answer, and that's it for this paper.